In the next section, we'll look at a new proposal for a complexity class against which we can try to prove hardness for parameterized problems in the hope that this is a bit more suitable to show that certain problems are hard, for which that isn't a trivial statement. For the p-coloring, graph coloring problem, we had this fact that it's para-NP hard because it also is hard if the parameter is fixed at 3. So here we want to try to include problems where this alone is not the case. So a fixed parameter doesn't make the problem hard, but it overall doesn't seem to allow an FPT algorithm. For technical reasons, it seems working with Turing machines for defining this class is not convenient or causes more problems than it solves. And I mean, in a way, this was just what I said before. Para-NP seemed like a natural definition, just replacing deterministic FPT time by non-deterministic FPT time. But it is, in a way, a too powerful class. So hard problems are too hard in our case. And for technical reasons, Turing machines seem not to work well. I think there's no great justification other than that. So we'll look at some slightly different models of computation, but also are fairly easy to work with. One thing I wanted to say here is we will restrict our study here. We'll look at parameterized complexity classes to the key tools to prove that a problem is unlikely to have I guess there's some word missing. Is unlikely to allow an FPT algorithm. If you want the structural complexities, say, study finer distinctions between problems, you could go further than we go. On the other hand, I also didn't want to just use reductions. One alternative in complexity theory would be you just nominate your favorite hard problem, the one that seems convincingly hard to you, and you show that the other interesting problems you care about can be reduced to this problem so that they are harder than a specific problem. So here, for example, we could just say that the parameterized click problem seems hard. Let me use the proper font. And then try to reduce problems to just to that. So we could try to establish say, let's write it properly. So you show that some problem you care about is at least as hard as the p-click problem, and then just stop there and say, yeah, it seems nobody knows how to solve p-click, so I'm going to stop looking for fixed parameter tractable algorithms for A. It seems unlikely that they exist. But this is a much weaker statement than what we are used to from classical complexity theory. Normally, we also do just a single reduction like this, but we pick a problem here that's NP complete. And so after we've done that reduction, we don't just know that some new problem A is harder than some specific problem that we picked, maybe 3-SAT or whatever reduction partner you used. But because that problem was NP complete, you know, it's this new problem A is harder than all the problems in NP. Harder in the sense of everything reduces to it. And that's a much harder, a much stronger statement, because it means your new algorithm doesn't have this algorithm, this efficient, your new problem doesn't have this efficient algorithm unless all of these others also have one. And if we were just to do this, it would be a much weaker theory. We would only relate problems to individual other parameterized problems. So that's the two extremes. One would be go full on the complexity theory and study all the classes and their hierarchies, which might be suitable for a specialized complexity theory class, but I feel here would lead too far. On the other hand, I didn't want to just say, okay, let's pick a magic problem like p-click and just proclaim that this seems hard. So I'll try to do some middle ground. The implication of that is that some of the definitions are not the original definitions of the classes we were studying, but rather they're alternative characterizations that people have proved about those classes. And they overall make a round picture, but they don't exactly correspond to the sources where it's taken from. It kind of combines different results. It's just a little disclaimer I wanted to put out there. So if you read up on some of these details or dig a bit deeper, you'll find that I'm renaming a few things. But the essence is the same. What we want is some hardness class. And let's name the beast. It's going to be W1, which is not WP that we'll see in this chapter. So there's one more step to go. So the goal will be to prove W1 hardness. And I'm not saying completeness, because for some problems that wouldn't be true. We'll only show hardness. For some problems, it's also completeness. For others, you would have to go a little higher to W2 and so on. But that part is this first bit where I'm not so interested in. If a problem doesn't have an FPT algorithm, how exactly it fails to have one, I think is slightly less interesting than the fact that it doesn't admit one. We'll maybe see some other techniques later. The board is really annoying. Should have told me that you can't read the last line. Okay, that's for the setup. So if we're not looking at Turing machines, what else is there? Well, many things, but actually we see an old friend again. For some of you, it's the random access machine. So if you want, we can say it's the word RAM. Now there's an important additional letter here, the NRAM, which stands for non-deterministic, right? So it's a word RAM, which just means it's a machine that has a long array of memory cells. Each memory cell can hold W bits, and we're supposed to interpret this as a number, an integer. And we can do the usual arithmetic operations on integers. We can also do bitwise operations, like a bitwise and all these things. So just to recap there, we've had it at the very beginning. So there's a large memory with just indices. And the important part is that these are really also numbers. So you can use indirect addressing. You can use the contents of one register to tell you what memory cell to read next. So you can do pointers. Right? So we have these. This is essentially unbounded. It's as big as you want it to be. And you have a finite number of registers. say 100. It doesn't matter exactly what the number is, but it's fixed and independent of the input size. And then you have operations for loading pieces. You can read a memory cell and load it into a register. You can write back to some memory cell, and you can give the address that you're writing to as the content of another register content. And you can do arithmetic operations, and you can do the usual comparisons and conditional jumps. That's just a reminder of what the word RAM model is. Now, there's an additional operation. That's the important bit from the N. We can non-deterministically guess a number. So there's a new operation. It's a fictitious operation that real computers cannot do. But you can say this register non-deterministically should now contain a number between 0 and some upper bound that you give by another register. And this is the machines that we're allowing our algorithms to use. Now again, remember, this is like NPs, like non-deterministic Turing machines. You're not supposed to build this machine. This is an overly powerful model that we're gonna work against. Then we'll say such an NRAM decides a parameterized problem, language and parameterization, in the usual way, like how do we define acceptance? I guess we have some output register, and that contains a 0 or 1. And we call such an NRAM kappa restricted if its running time is FPT for the input. This part is the same as for Turing machines. Also the space, I mean here, okay, memory cells, I would really want to say. The space usage is kind of following from the time. You don't even have time to touch more than this. But it's maybe less obvious than in the Turing machine. We also put a bound on the numbers in the memory cells. So in a way, you could control this via W, but it's more convenient to directly just say the numbers that we have are bounded in terms of the parameters. So in a way, the traditional is just log n. With the parameterized problem, we would say W can be a power polylog n, and no, sorry, it's log of a polynomial. That's just log n, and some arbitrary function of k. If you take the log here, it doesn't really make a difference. Okay, so these are relatively natural things. That's just what an FPT algorithm means on a word RAM as opposed to a Turing machine. But then there's this second requirement, which is important, kappa restricted. The number of non-deterministic guessing steps, these new operations, the fictitious magical operations, they're bounded in terms of the parameter. You cannot do arbitrarily many of those steps. Okay. So how does this compare to Turing machines and FPT running time? Especially if you compare it to para-NP. There we didn't have step 2. We said non-deterministic Turing machine with a certain running time, but it was allowed to do a non-deterministic step each time it does a step. And so this restriction 2 here is the key difference. Now you could have tried to do the same in a Turing machine, restrict how often it does a non-deterministic step. The problem there that makes this inconvenient is that in a Turing machine, the non-deterministic guesses are actually finite, they're bounded. For a given machine, there's a given number of states, and everything's finite and fixed, the alphabet symbol, the number of states, and all that. it cannot depend on the input size and certainly also not on the parameter. So these non-deterministic steps would only choose among a constant number of different alternatives, fixed and constant. And that turns out to be just an annoying model. You would have to somehow then translate that to allow a certain number of steps, which should somehow be able to depend polynomial on the input size and arbitrarily on the parameter. It gets very messy. And here is easier because you say the non-deterministic step is a little more powerful. It's allowed to guess a number that is unbounded in general. You can restrict it harsher on how many of those you do. So what I'm saying is the details of how the model works for this lecture are not so important. The key step is the non-deterministic guessing step here. It's more powerful. Okay. Then we can define a new class of problems, which is called WP. And the naming will become a bit more clear in a moment. It's the class of all parameterized problems, L kappa, that can be decided by such a non-deterministic RAM. Exactly as we defined it, kappa restricted, which means FPT running time, FPT size of the registers, and at most a function of the parameter many non-deterministic guessing steps. Okay. That's a class of problems. So you can think about what kind of problems are in this class. So how about say our clique problem? The point is, let's try to implement the brute force algorithm on such a machine. So of course we need to use the non-determinism. And what do we guess in the clique problem? Well, k vertices. A subset of size k. How many non-deterministic steps do we need for that? Exactly k, because where we have numbers between, say, 0 and n minus 1. Okay. So we're using the non-deterministic step to tell us which vertices to pick, and then we're just verifying that it's a clique or check. Might want a name for this set. And that actually takes only time bounded in terms of the parameters. So the whole problem hardly depends on the input size now, on this NRAM. Only this upper bound for the guessing step really needs the input size. And so, well, I guess we can, depending how the graph is represented, maybe we have to walk through the graph to count the vertices. And so the running time would be linear in n, say. Let's be generous and say n plus m only really needed to count the vertices. And then we have k non-deterministic steps. And then we have k squared to verify all the edges are present. Now, this is assuming we have an adjacency matrix given, but in this initial time, you could also take any other representation of the graph and transform it into an adjacency matrix, I guess in n squared time. Let's not get fuzzy about the details. Let's just put n squared here for number of vertices. The details here don't matter really. My point is, I just wanted to show you an example of how programs in this WP class look like, because I think it's fairly natural. Apart from this guessing step, everything else could easily be implemented, and the plain brute force algorithm works. It's just that this guessing step now allows us to use the non-determinism in actually a more convenient way than on a Turing machine. It's in a way, it's a more powerful model. It's more convenient to program. It is a bit harder to use in proofs. Okay, certainly this is an FPT time, and the whole thing is kappa restricted because we only use k guessing steps. So that shows, I guess I posted as a question, so the answer is yes. And most of the problems we had can really be cast in this way. In particular, all the problems where we had, as part of the guessing, pick a subset of certain things where the subset size is bounded by the parameter. Right? All these graph problems of the flavor of click and independent set, and yes, also vertex cover, less interesting, dominating set. What else did we have? All of them have this property that we're just guessing a subset of vertices, and we can do that in that same way. Okay, so that sounds like a reasonable class. To work with WP hardness, we would need a complete problem, or at least a problem that all of that class can be reduced to. The definition of hardness and completeness is exactly the same as always. So a problem is WP hard if every problem in WP can be FPT reduced to it. And completeness adds the requirement that the problem itself is in WP. Now, what could such a complete problem look like? It would somehow have to work. So all we get if we say we have an arbitrary problem in WP is there is such a kappa restricted NRAM. And from that, we somehow have to get a reduction. So the satisfiability problem popped out as the right answer for classical Turing machines, because you can simulate in a Boolean formula how a Turing machine computes. So we somehow need to do something similar here, but we also need a parameter, right? It needs to be a parameterized problem. And if we take sat and look at the number of variables, we know that that's in FPT, right? So that's not going to work. Okay, I answered my own question, but yeah, I guess you would have remembered for sure. So that cannot work. Maybe as some other variant of sat is more promising. The key feature we have is we can guess numbers, subsets. That's what we've seen in the click example. But that doesn't seem to work too well with sat. Or well, what would that mean in sat to guess a subset? Well, we can guess a subset of the variables. And so a somewhat natural restriction would be that we guess which variables are true, but we bound the number of variables that we are allowed to set to true. And that's the weighted satisfiability problem. Okay? I think I initially mentioned this when we started talking about fixed parameter algorithms as one option for satisfiability, and at the time I didn't try to make it sound like a natural thing. But here, if you come from this NRAM definition, maybe it's not so unnatural that this might work. So the problem is defined as follows. You're given a Boolean formula as for satisfiability in general, and also some threshold k, which is our parameter. And the question now is, can you satisfy the formula with an assignment that, okay, let's be strict, that sets exactly k variables to true? Okay. And we call that the weight of the assignment. That's just the name that gets stuck. I don't know. The number of variables that are set to true. So let's show that this is indeed in WP first. So what would we do to solve that problem? Well, same algorithm as for p-click. Because you're restricted to a weight k assignment, you can guess the subset of variables that you set to true, and then you evaluate the formula under that assignment and see if it is indeed true. Easy. What you can also prove is that a certain variant of this problem is WP complete. Now, in this case, I'll only sketch a bit the proof because WP won't be the final answer for us anyways. It turns out you cannot really make this work. So what we have to do, we want to simulate any NRAM, any, I guess, kappa restricted NRAM. To a weighted SAT problem. And if you try that with ordinary satisfiability, so the Boolean formulas as we know them, this seems not to work. Just because you don't easily get a bound on the weight of the satisfying assignments. But it turns out that there's a slightly more powerful model of satisfiability where this does work, although the details will lead us too far. I just want to sketch briefly what this talks about. And for that, we need to talk about Boolean circuits. I don't know if people have seen this. Maybe in the more technical parts of computer science, you're more used to working with these. The theory version would be you have variables as starting points. And these will have some Boolean value, true or false. Get it a little bigger. And then with the formula, we would normally use, well, we would write the variable many times. Here instead, we can have and OR gadgets, and they can just use variables as inputs. I'm making up this formula now. It probably means nothing interesting, just to make the point. And here you could take this, and this, and this. And so the edges have a direction. They go from left to right in this picture. But the key point is I can use some part of the formula many times. In a circuit, the output, let me maybe add the directions explicitly. So the point is, what's the difference between circuits and formulas? circuits can be much more compact. Because if you spell out what I've written here as a formula, okay, I would have to say what the output is, I guess. That's still missing. So this is a single thing that goes in here. And that's not used. That's a bit pointless. Okay, probably this formula is completely nonsensical. The point is, you have an input variables as you have for a formula, and you have a single output. But within the formula, you can have sub-expressions. For example, this sub-expression x1 and x2. Oh, I haven't used any nots, right? That's not good. Let's include a not. This just has a single input and output. So there's this part of the formula x1 and x2, and that's used twice. In a formula, I would have to copy it and write it twice. Whereas in the circuit, I can reuse the output of this single gate several times. And that means you can have large parts that are reused, and then the larger reusing parts are reused again. So in general, circuits can be exponentially more compact than a formula. If you had to spell this out as a formula, it might grow exponentially. Which also, then on the flip side, means working with circuits as an input is often much harder because they can specify more complicated functions with less encoding size. And so you have less to work with because the encoding size is your input size from which the runtime is determined. Okay, so that's a formula. You can always interpret, sorry, that's circuits. You can always interpret a formula as a circuit by just writing it as a tree. So maybe that's worth stating, right? But there's many more tricks you can do on circuits. And the key that we're using here is that you can modify them so that they're satisfiable with a fixed weight. So the idea of the reduction we're given an arbitrary problem. We have to show an arbitrary language, L kappa in WP. The claim is that this reduces to this, this problem. So the circ just stands for circuit, just in case it's not circle, cycle, or anything like that. The idea of the reduction is from this, we get, there's an NRAM for solving this. Then we simulate this NRAM with a multi-tape Turing machine to get closer to formula. And then we simulate this Turing machine by a Boolean circuit. That's a similar reduction, as a similar construction as for the proof of the Cook-Levin theorem. And then comes the trick on circuits, which makes the whole point about circuits necessary. We can find the circuit D so that C is satisfiable if and only if D is satisfiable with weight K. So several of these steps are not so clear, right? I didn't tell you really what multi-tape Turing machines are and how we can simulate the word RAM operations. And I also didn't tell you what this trick is. That would lead too far. So it's kind of just a brief outline, roughly what this looks like. Let's claim that's a bit of a proof, but that's roughly what it would go like. So it has similarity to classical complexity in some sense, but you have to do a few further steps to get the weighted satisfiability. The point why I think it's not worth digging through the details here is that this is not the final answer. Yeah, I don't think I have a nice example here. The problem with WP is that it still seems too powerful. The key problems that we were looking at, say p-click, is part of this class. But it seems that we cannot actually reduce this problem p-sat circuits to p-click. In a way, the circuits are too powerful, and this WP complete problem is too powerful to be simulated with something like p-click. If you were wondering how to do that, I guess it's subject to some complexity theory assumption. It isn't possible. Weighted set of circuits. Did I put that in normal parentheses? Okay. So the not here is important. I don't know. That doesn't seem to work. So we found a class with a natural complete problem, but it seems it's too hard a problem.